All right. Tonight I want to talk a bit about things that ultimately will be helpful for the rest of TMA1. Last session, no doubt you'll remember, we spent a fair bit of time on integration by substitution, starting with the chain rule and how it might help us to integrate difficult functions. Then we talked a bit about single variable or univariate distributions and a little bit about linear transformations. And then I gave some examples out of the module materials and past exam papers, and we talked about, finally near the end, question 3 on TMA1. Tonight I'll talk about moment generating functions again, marginal densities, do some examples, a little about cumulative and perhaps a bit more than a little, talk about cumulative and conditional distributions. I don't think we'll actually get it. Briefly we'll mention Bayes' theorem, and we'll make sense of 2 TMA questions, that is questions 1 and 2 on TMA1. Right. Moment generating functions. I thought it might be useful to look a little bit at the sort of general intuition for these and a little bit about the background of where they come from. We want to turn a PDF into a different function effectively, and it sort of exists in a different universe. It's the thing we're going to turn it into, or the thing we're going to use to represent it, is not a PDF. Now, it's not the observations on a random variable, but they're observations on a new variable t, where the variable t is this counter, if you like, inside this expectation function. Why might we decide we move away from the probability density function into this other rather strange thing? Well, largely because the sort of thing we move to has useful properties. Perhaps they're not quite so useful as they used to be, but they still get to be used and are valuable for us. The moment generating function, the thing we turn our PDF into, has some useful properties. If we differentiate, the moment generating function, we get a sequence of functions whose values at 0 are the raw moment, the mean, the second moment, therefore we can get the variance and so on at higher order moments of the PDF. And as you'll see later, we will use knowledge of these moment generating functions in proving a form of the central limit theorem. Right, now, we know things that if we have independent random variables, then the moment generating function of the sum of them is the product of the moment generating functions. That is, the moment generating function of the sum of them is actually the product of the moment generation of one with the moment generation function of the other. Now, I'm going to work through a proof of this because it'll help you understand how the answer to one of the TMA questions should be structured. Right, the first thing I'm saying about how we proceed is we start with one side of this formula, and I've started with this side. And we just make changes in it to reach the other side, the right-hand side here. So we are going to start with this, and then we're going to do things to our definition of that until we get through to the thing that was on the right-hand side in the formula I've just talked about. What you will need to do is you need to give reasons for each change that you make, and One thing you shouldn't do is abandon working from, well, in this case, left to right, and then decide just start working from right to left. That's not going to make for a satisfactory proof. People to read what you've got and so on. So, let's look at it. Step one. We can write down the definition of the moment generating function of the sum in terms of the definition of moment generating function. It'll be the expectation of this strange transformation of the sum of the two random variables, as I've shown you there. And that's in fact the reason for why it happens. It's just the definition being applied. And that in turn, because we know the properties of exponentials, can be written as the product of two exponentials. So there we are. Here's our first line with an explanation. The next line I haven't given one because it's simply a property of exponential functions. Then the next thing we do is we can write the expectation of those products of transformed random variables. We can write it as the expectation of the two products multiplied together. Why? Well, it's a little bit more complicated than the previous steps, but not much. It's got something to do with linearity of expectation because we're told that y1 and y2 are independent. And if we look at section 4.4 in unit 3, we're told that we can write them like that. There's a little derivation there, but we don't need to reproduce it here. Okay. Now that in itself is about as much as we need because the next thing we can write is we know that that's a moment generating function for y1 and that's a moment generating function for y2. So we can write our next line. It's that. And I've put a y there just for completeness. Well, the y translates into saying something along the lines that we're just applying the definition of a moment generating function. Now that's so clearly, easily understood, and it's a rigorous proof of the desired property we're after. That we started with one side of our equation and worked our way through to the other. Okay. And surprise, surprise, we've got something to say to you about TMA 1, question 1. So you're going to use a method of proof as I've just sketched out in the previous slides. Okay. And not surprisingly, we're going to make use of linearity of a transformed random variable, and in particular, in an expression involving expectation where there is a constant, then we can write the expectation as the constant times the expectation of the random variable. Okay? So that should be enough for you to deal with TMA 1 pretty easily. Are there any questions on that? No? No questions? No one putting a hand up? A couple of people have given me ticks, so I guess that means that plus the silence means that people are happy. All right. Now let's just, whoops, sorry, I'll just minimise that again. Whoops, what's happened to my cursor? Let's just put a little more flesh on the bones of the definition and how we come to think about it, think about these moment generating functions. Now we know that the expectation of a random variable can be written like that, in terms of some PDF. And multiply the PDF by the value that the PDF takes, and that lets us get a mean at the end. But suppose we had some more complicated function. Instead of x, then the same thing's true. We can write down what the expectation of the transformation of it, by the integral. Generalize that slightly. Support this thing here. Then we can write the expectation of some transformation of the random variable as the transformation of the values times the PDF. But then, if we decide that we know that we've got for this potential transformation involving t, then we can write the moment generating function as the expectation of either the tx, with just expectation, just this strangely transformed variable. Just in it now, as I think I mentioned before, for each value of t in whatever the range of values of t is that's appropriate, we're actually moving away from thinking about the random variable, thinking about things to do with this counting variable t. And that moving away towards t from the random variable is what I was saying to you earlier. We're moving away from, excuse me, the universe of random variables to some other universe. And the other universe is a universe to do with knowing things about certain sorts of functions or certain sorts of transformations of functions. And that universe is the universe of what's called Laplace transforms. Now, we use them here because we're interested in getting an easy handle on things like higher order moments of a function. But in other parts of the mathematical or the physical sciences, we actually use them, these Laplace transforms, very widely to solve differential equations that come up in engineering and bits of mathematics and physics, where we're interested in variations in space and time. Now, underneath these Laplace transform things, there does lie some quite deep mathematics, but we don't have to worry about it, fortunately. A moment generating function is really just for us a sort of portable way of carrying around all of the moments of a random variable that we might want to get. Why is that worth our while to know? Well, it's sort of a bit historical in a sense, because back when these were first issued in statistics, wanting to know what these higher order moments were, higher order means and variances, whatever you want to call them, this was first an issue back at a time when it was difficult for ideas to be communicated between people. Knowledge of integration wasn't so widespread, and that goes back to when statisticians were first interested in moments, and that's about 150 years ago. And moreover, doing numerical calculations, we didn't have calculators and computers like we have now. You couldn't do these things numerically. So having some handle on how to generate the functional form that was a higher order moment was really quite valuable. As I said to you before, these Laplace transforms, these things that underpin the moment generating function, the idea was to turn what were thought to be pretty intractable, difficult functions into easier ones to handle. And in a way, that was what the statisticians were up to. I guess I won't say any more about that. I've just given you a couple of notes there. What we actually do is we start with a PDF. We get the moment generating function. Then the raw moments drop out. And for us, fortunately, they drop out from not very complicated calculations. I'll show you an example of two in a minute. So we don't need to do the mathematics. We don't need to worry too much about, which sorts of mathematical space of functions we're dealing in. We just need to do the mechanical things. So we've got an easy handle on what higher order moments are. Well, if you look in section 2.8 of Unit 3, is it? We know that the moment generating function for a random variable x can be expanded as the right-hand. Looks a bit of a mess, but Taylor expansion, something that's used very widely. Make a derivative, say the rth one, the derivative of this one up here. And we were to set the value of t to 0, then we would see that because when we differentiate r times, all of these terms down here would drop out. We'd just be left with exponential value of x to the r. Then we can see that we would get the rth moment, the rth moment of x by taking the rth derivative. That's what the little r up there signifies, and set to be 0. So, for example, well, what I've just said to you means that we should just take the first derivative, right, where the little dash means first, of the moment generating function and set all the values of t to 0. Well, if we did that, if we differentiated once with respect to t, we'd lose the 1. That t would disappear and we'd just have expectation of x. And there'd still be powers of t all the way up here. And when we set t equal to 0, they'll become 0. So we'll be just left with the first expectation. Okay, so that's saying to us the expectation of x, the population mean we got as the first derivative, the moment generating function. Equally, we can get the variance of the first variance of the random variable by taking the second derivative, which means we'd only wind up with that term there when we set t equal to 0 less the square of the first moment. And that's just harking back to the definition of what variance is. Okay, are there any issues with that so far? Let me go back so I can see if anybody's putting their hand up. No? No problems? Oh, hang on, there's a comment. No, there's not. No, okay. Oh, hang on, sorry, Philip. I see you've said something. Oh, no, it goes back a bit. What are we saying? First line, slide 11. Yes, you're right, Philip. I've got a capital F where I should have a lowercase one. Yeah. There. That should be all right. Anything else? Now, as I did in the last session, I'll take various things off various. There's let X follow the Pareto distribution. And that tells you what it is. It's that formula there on X greater than 1, where you're told that the parameter beta in it must be positive. But we're going to further constrain it for this question to be bigger than 1. So make sure you read the details of each question. Then it says choose from 6 options that are given to you. Find the mean of this distribution. Okay, well, for beta bigger than 1, we know that the expectation is going to be the integral between 1 and infinity, because that's the support of the function. Okay, there. Explained to us there. Why do we use this equality sign? Because we're just going to write down the definition of the expectation function, which is going to be the integral over the support of x times f of x. We can stick in what we know f of x to be because it's the Pareto. It's this beta over x to the beta plus 1. We can gather terms together. That x and that x to the beta plus 1 will give us a bit of cancelling. So we're talking about x to the beta, x to the minus beta. We can knock the beta out as a constant. Evaluate the integral by looking at the antiderivative, which must be the thing inside those brackets, and put in the limits for the integral. Okay, evaluate at infinity, which I'll come back to in just a moment, and the difference from when at the lower level when x is 1. Now, why is it that we get 0 for the value of the function when x is arbitrarily large? Well, if beta is bigger than 1, then 1 minus beta must be negative. Okay, so if you put in a really big number, you're talking about 1 over something that's big. 1 over something that's big approximates to 0. So that first limit of integration, when we stick it into the antiderivative, gives us the value 0, which is what I'm saying down here in this box. And so it becomes easy enough to see that we're going to get the ratio of beta to beta minus 1. So there's a few free marks in there, isn't there, if you know just a little bit about integration and just a little bit about what the expectation function is. Get you started on your exam paper quite nicely. Then let's look at a question of the 2012 paper. Again, question 2. Suppose we let x follow the power distribution, which is a slightly different version, with beta bigger than 0, and it's only defined for x between 0 and 1. Then again, you're given 6 options, and you're told choose the option that gives the formula for the third moment. Okay, expectation of x to the third. Well, the way you proceed is you've just got in situations like this, do the algebra to try and calculate what the third raw moment is. Good question here. What other moments are there? Answer: the central moments where you move things so that they're centered on the mean. And there's material in the notes on that, in the lecture materials on that. Right, so the definition of the third moment is that, given what the support of the function is. So notice the x cubed here, reflecting that cube there. Stick in what the PDF is, do a bit of simplification over the x's, pull constants out, and get the antiderivative of the thing inside the integral, which is that. Okay, that's the answer to that question. The result of doing that integration is the thing in the brackets there. When you stick in the limits, beta's 1, subtract from beta 0, it evaluates to beta over beta plus 3. Again, Relatively easy marks to be had on the exam paper. Now, let me just pause for a moment while I just check what this is about. Sorry. Oh, okay. Yeah, 2.9 in Unit 2 has got quite a lot of calculation associated with it, but to sort of summarise what it's saying to us is it's telling us things about the moment generating function of the standard normal distribution. First thing we know is that the first moment turns out to be just that, and the details are given inside example 2.9. If we differentiate that once, well, composite rule says to us that the exponential function just is itself when it's differentiated, but the thing that's the exponent is a function of t, half t squared. So when we differentiate that, we'll just get a t, which is the term that's sitting here. So we know mu is the first moment. That's what we normally denote it as. And we know from what we were just talking about earlier that we'll get it by taking the first derivative of the moment generating function and evaluating that at 0. That is this thing. Well, there's the first derivative of the function without t being set to 0. If we set t equals 0 on that, because of the t here, we're going to get 0 as a value of the moment generating function, and therefore the value of the mean in the standard normal distribution. Now that's fine, isn't it? Because we know that a standard normal distribution has mean 0 because we've centered the thing at 0. Now, the second moment we get by differentiating this, and it's again, well, it's not again, sorry, it's a product of two terms in t. If we take the first term, well, differentiating t gives us a 1, and then when we come and differentiate this other half, oops, the other part of it, sorry, oh, can't get it, the bit without this t in this product, sorry, then we'll get another t from repeating the derivative we did the first time. So if we take this second, sorry, if we calculate the second moment as the second derivative of the moment generating function evaluated at 0, well, that's t is 0. Well, we put t equals 0 in there, then we're just going to get 1 times whatever's out here and whatever's outside the bracket when t is 0 is 1. So the second moment is going to be 1. Well, we can then do what I did before, which I did in shorthand. We can calculate the variance. It's the difference between the first moment, the second moment, and the square of the first. Or if you like, this, which is more accurately what I said. Well, we know the first one is, the first term there is 1. It's that one. The second term is 0 from up here. Stick it in there. The difference between 1 and 0 is 1. Now that's okay as well, isn't it? Because we know in a standard normal distribution, univariate distribution, the variance is 1. So, yeah, a little confirmation there through that example that the moment generating function idea works in the case of a distribution we know pretty well. Now, well, I'm sorry, before I go on, are there any issues there? Any questions anybody has on that point? No? Everybody's very silent. I'm either being very clear or very boring. I'm being very thirsty, actually. sitting here swigging water, or a few people saying clear, so I'd perhaps just roll with that. Okay, Richard. Okay, we'll just turn our attention to something that's a little more intricate. I want to talk about marginal distributions. And I've just given you a little schematic there that I got from somewhere or other that shows that for this two-dimensional distribution here, this thing here, there's slightly different shapes when you project onto either axis. Well, of course, we're going to have to talk about bivariate densities. That is where there's two random variables involved. And the way you get from a bivariate density down to a marginal density is you integrate. In the continuous case, that is. You integrate over one variable to get a univariate density in the other variable. And we call it the marginal density. Why? It sort of comes from the days when people used to calculate tables, values, so that across the rows might be the variable y, down the columns might be the variable x, and you might get the margin with respect to x by adding across the y entries in the table. So what you're doing is you're sort of adding across the rows, and they would say, we'll write the answer in the margin of the page. Hence the name, marginal density came up. So if we've got a function that's integrable, continuous if you like, a bit more restricted than it needs to be, but we've got a function that we can integrate. If we would integrate, that is, if we were effectively the sum over the y values, we'd get a distribution that just depended on the random variable x. So we'd actually get the PDF for x. And if we were to integrate over the x values, or that is sum down the rows, then we'd get for a particular value of y, we'd get values of the marginal distribution with respect to y. That's univariate distribution. That is, you hold one variable fixed temporarily while you do your integration, say y, and integrate with respect to the other, say x, to get the marginal distribution for y. That is, in this notion of finding marginal densities, we're really getting rid of the dependence on one variable. Okay. Now, in the materials, there is this rather daunting definition, but all it's saying is what I've said to you in the words of the previous slide. Right? To get the marginal with respect to x, you integrate over y. To get the marginal with respect to y, you integrate over x. And there's some rather nice graphic help in the notes. Here's two examples of bivariate density functions. One there at the top here, one down here. They look rather different. And over here we're showing the projections from looking down above the so we're looking down in this direction. You can see that bobbing up and down the cursor. What do the marginals look like? Well, I've done that here. Here's the projection from above for the first of them. And then the marginal with respect to x is this rather fuller sort of inverted U. And the marginal with respect to y is a rather narrower distribution. And similarly, we can do the same thing for the other case. And what I've tried to indicate to you is that the contour plots of these things with the red arrows and the marginals we're interested in are things like these. Okay. Now, let's go back to the standard bivariate normal to see how all this works in practice. The standard bivariate normals support that consists of effectively 2 copies, or all of the values caught up in 2 copies of the real line. And we have some correlation between the variables, which is specified by correlation between -1 and 1. And the formula for it, a bit of a mess it looks, isn't it, is that. Now in example 3.2, it works through how to calculate the marginal with respect to x and the marginal with respect to y. And I think this is right from memory. The way it's done is they use, because we want to integrate over y, they've changed it to v as a variable, just let us sort of keep in our minds that that's the things that vary over time. And similarly down here, we want to get it with respect to u. And it turns out when you do that, you get, surprise, surprise, copies of the standard normal in each case. Okay. And I'll leave you to look at that example to see that result. Yeah, well, here's what I've just said to you. The marginals of the bivariate standard normal PDF are univariate standard normal PDFs. The mean's 0, standard deviations are 1, because you can read that off the form of the expressions back here. Okay. But this correlation row reflects some sort of correlation between the 2 values of the 2 random variables. We will see a lot more of this as we work our way through later sections of the course, but there is one sort of indication in the exam question that sort of helps us see just what the relevance of the row is. This is an exam question from 2015. In fact, it's question 5. What we're being asked is, we're going to think about the bivariate normal, which has got these 5 parameters that they quite tastefully give to us, right? 2 means, 2 standard deviations, and a correlation. And then we're told to choose 2 options out of the list of 6 that are actually false. And there are the 6 options. Now, a bit of a mouthful to read through, but as it happens, all of the information you need to do this question is actually given to you in the useful results and formulae at the back of the exam paper. And if you like, I've given you some references also there to where you might go and look in Unit 3 materials to see the same sort of thing. Now, I'll not take you through it all, but, well, I suppose just start a little bit, I think, rather than doing the whole lot, but I'll do a little bit of it. Option A has got to be true, doesn't it, because of what I've just been telling you. The marginal distributions and the conditionals which we'll come to associated with the bivariate normal are going to be univariate. That's what we saw in the case of the standard normal, so it tells us what's going on. So B can't be false. Option B, expectation of y given x. You can look this up in the back, useful results and formula. No, that's got to be true. And then when you look at C, again from reading the back of the materials, reading the materials at the back of the exam paper, the covariance matrix isn't quite that right. They're telling us to look at the covariance matrix, yet we're only seeing correlations there and there. That's a bit of a flag that there's something wrong. And the reason's there, right? Concentrating on covariance, the covariance in the off-diagonal terms is not rho, but row times the product of the variance in the two variables. Similarly, as you work your way through it, D, E and F, the correlation matrix has got to be what it should be in D. E, the bivariate standard norm, is a special case of the bivariate general normal with the mean set to 0 and the standard deviation set to 1. We just know that, don't we? Bit of practice over the years. And then finally, you can look in the back of the formulas at the back of the exam paper, and you can see that that's not going to be true. That is, we're told that the variance is not sigma y squared, but it's 1 minus the square of the correlation between them. So in fact, the correlation between the two variables in the bivariate normal distribution does have an important role. It's a thing that specifies the variance in the conditional distribution. Oh, right. Yeah, these next two slides are a bit of a test because I'm looking a long way further forward in the materials. I'm looking forward to when we're dealing with Bayesian statistics and how we apply Bayes' rule in general. I didn't really want you to work through it. I suppose what you should do is plant in your mind the idea that this and the next slide are giving you a solution to an example that involves Bayes' theorem, Bayesian statistics, and therefore the posterior and the prior and so on. But what I wanted you to notice about it is that this question, and the language does look pretty odd, I'll admit to you at this stage, but the thing I wanted you to notice was that while we're going to look for the mean of a particular distribution, this thing called the posterior, we're actually dealing with conditional distributions. And the next slide takes you through the detail once you've done the sort of the theoretical analysis back here. Don't worry, we'll get practice at things like this when we come to TMA 3 from memory. But by the time we reach that, you'll be well steeped in the language that underpins the sort of statement here. As I say, I just wanted you to note that later on in the exam questions, you could find yourself dealing with things that require you to have a good knowledge of things like the marginal distributions and the conditional distributions. Right, that's the end of that first part of my presentation. Are you reasonably okay with that? Is there any questions? Are there any questions? Sorry. No? Yeah, Richard, there's a lot to take in, but I think I've got it fairly pointedly directed at the sort of things you need to know. Okay, Philip, Richard, thanks. Trust me, Richard, it will be. It's just a matter of persevering with the module materials and trying lots and lots of examples. Okay, well, I'll move over now and look at a little part of my next presentation. We're going to get through it all, but I'm pretty sure we won't. Let me just find it. What do I need to do? Oh, what's happened? Back to here. I want to share that screen anymore. I want to share the following one. That one. Share. Oh, what happened there? Can you see it? Are you all able to see it? just check that you can. Yeah, right, okay, just hang on a minute while I play around a bit more. I'm a bit surprised by this myself. What is going on? Stop sharing for a minute. Now I'll try and share again. Right, can I ask again? Can you see, and we go back to the start, can you see the slide that says M347 Adobe Connect 2 Part 2? Much better. Much better. Right. What I want to do here is concentrate on things to do with cumulative distributions. Let me just get this in my own head for a moment. Oh yeah, okay. What I've got here is univariate with bivariate. Now here's the definition in the univariate case, definition in the bivariate case is an extension, a double integral from a single integral. And we're one on instead of just one restriction as in the univariate. And see the properties by looking at unit 2 for the bivariate thing given in unit 3, where that reference is. Now, in the what the probability that's mopped up between 2 points. But in the case of the bivariate case, it's rather more complicated, isn't it? And it's not just simply a definition between two terms. That is the difference between two terms, but we've got another term to extract. And I thought it was probably worthwhile letting you see why that arises. Now, one way of seeing it is you can go and look at Screencast 3.1, which is quite nicely made up. And I just pinched one screenshot from it there. But let's just see if we can't construct it, why it turns out to be this rather more complicated term. Right, we're interested in the probability that's mopped up between limits on one random variable and limits on the other. The limits on the random variable x between there and there, and the probability that's mopped up between there and there in the case of the second random variable. Right, well, let's begin by figuring out what the total area is up to our upper limits, both for y and x. And the cumulative distribution in that case is obtained by looking at the probability for x being from 0 up to the upper limit for it, b, and y running in value from 0 up to its upper limit, d. And that's the orange shaded, I suppose it's orange shaded box shown there. And you can see that's not the area we're after, which is this black rectangle inside that orange mess. Well, suppose we subtract the bit of area to the left that we don't want. Now, if we subtract the area from x up to a, and the area from y up to d. We're going to look at the area that's mobbed up from here up to a, and the area that's mobbed up from here up to d. That's right. Got that wrong for a moment. So we're going to, if we overlay the bit that we've now subtracted from our original orange area, we can see we're still not quite there because we've got this region down in here, haven't we? So we've got some more to subtract to get to the area we want. And we don't want that bit there that's got the text over it now, and so that's eliminated by taking the difference between two other cumulative distribution values. We don't want the probability that's mopped up between A and B for X. We don't want the variable that's mopped up between, between B and C. Well, what am I saying? We don't want the area that's mopped up between A and B. We don't want the area that's mopped up between from between 0 up to C. So we want to get rid of the area that's between A and B in terms of X, the height, up to C for the variable Y. So there's the source of the second term that we need to get rid of. When we subtract it, sure enough, we just get the dark rectangle that we wanted. Now, if you haven't been and studied the screencast for this, go and have a look at it. Just play around and let it run out. I think you'll find it quite helpful. Okay. Or you might find reading over my little graphic demonstration helpful. Now, let's look at some questions that are somewhat favoured by the examiners, it would seem. In the exam in 2015, question 3 on the paper was the one that's shown here. Looks a bit odd, doesn't it? You're given X and Y independent random variables. They follow the same cumulative distribution with functional form F1. And suppose we define a new cumulative distribution based on taking the maximum values of either random variable. Then you're given 6 options, which are the ones over here. And they're asking us to find an expression for the distribution of the new variable W thing here. That is, by distribution, we're talking about figuring out what the cumulative density function is. Okay. Oh, what happened to me? I've hopped off it, have I? What happened? Oh, I've got the answers underneath, sorry. Now, there's a little trick in this which can be repeated in various forms, which is why I think it's the sort of question that's favoured by the examiners. We know what the new variable is defined as. It's the biggest value of either of the random variables. So if we have some value for that random variable, little w, then because that little w must be at least as big as the value attained by either x or y, then we can write that line there. X must be no bigger than w, and neither can y be any bigger than w. Now, we can use the independence property. We're told the x and y are independent random variables, so the joint distribution of them, this thing here, will be the product of the distributions of each when that's got a value less than or equal to y. But given that they've got the same cumulative density function, those cumulative probabilities will just be the same functional form in each case, the same CDF in each case, which can be written as the square of the given CDF. And the answer that matches that is that one in the bottom here. The correct answer is F. Now, it looks a slightly odd question, and you need to sit and think about it a bit, but once you get this bit of logic in your mind, you can apply it in a number of cases, although I'll show you shortly a case where you've got to do some other little tweak first. What's going on with this question? Oh yeah, okay. We're given a bivariate random variable, xy. It's got the same support in each of its bits, in each of its random univariate random variables. And we're told marginally y follows the exponential distribution. We're told what the parameters are. And conditionally, that is, getting the values of x contingent on y being fixed. It follows a normal distribution with mean y, variance 1. So it's this notation here in y1. It says choose from the following options, the 6 that are given there, what the joint PDF will be. Now it's a bit odd, isn't it? We're given a marginal and we're given a conditional. So we need to know something about how you relate the general distribution to having knowledge of a marginal and a conditional. That's okay because it's all over the materials. It's not in the usual results and formula, by the way. It's one of those sorts of things that a statistician's, I think, meant to know with his DNA. If you look in the unit materials, unit 3, 3.2, you can see that the general distribution, the bivariate distribution, it can be written in terms of a conditional and marginal. But having remembered that, you can then go and look up the usual results and formula at the back to write down what the conditional distribution is we're interested in, because we're told that that's to do with a normal. And we're told that the marginal is to do with, the marginal distribution on y, follows the exponential distribution, which you can look up in the back so you can get a form for it. Now, we're actually also told in the question to look for options associated with the core of the joint PDF. So it's okay that we've only got things that tell us about proportionally being related to these two functional forms, because that's what the cores are about. It's the essence, the bit that's varying. Okay, well, we can use the formula up here. Use the formula up there. Plug in the things we know about the what happened to me there? To cause, to write a term involving cause, run through a little bit of F. If you want to read more about how this works in practice, there's some further information given in Unit 3 in those places there. Oh, okay, this next one's off the specimen paper. We're again given independent random variables x and y. Again, they follow the same univariate distribution where the CDF is denoted as F1. So it's a question like that earlier one, except now we're looking at the minimum value is what defines the new distribution V. We're then told, find an option that describes the cumulative density function, for this new variable. And look, mercifully, we're given a clue. Start by considering 1 minus FV of V. Why? Well, when you do that, you instantly turn it into the form of the problem we did 2 exercises back. We were talking about the maximum of 2 random variables. Because 1 minus the minimum value must be the value that the new random variable is bigger than whatever the value is, in this case little v. So we must be talking about the probability that the minimum of xy is bigger than v. Well, that's going to be the same as finding the probability that x is bigger than v and y is bigger than v. So it's the same as the previous question we had. But now, because we've done with 1 minus f sub v, the cumulative distribution can be 1 minus f1, 1 minus f1 in each case, because they're independent variables and because they follow the same cumulative distribution. So the result's going to be 1 minus the f all squared. And that in this list is option D there. Okay, now is anything on any of that before I go on? Yeah, okay. All okay. Jesus, look at your finger. Okay. It's my son, by the way. Oh, okay. I've been waiting for you to type in to come up. No, but I didn't realise you're just telling, apologising for leaving. Thanks. Okay. Well, nobody else has said anything, so we'll carry on. In fact, I won't carry on for the whole 31 slides. I think I might stop a little early. Let me just check forward and see. Yeah, I might get down to slide 20 because I think after that it gets off and wandering off into... Yeah, it does too. We'll save the Bayesian analysis for later. Right, back to where I was. Well, this is me just revisiting what I've said to you in the previous part of this presentation on marginal distributions. You know, if we've got a univariate distribution, then we get that cumulative by integrating over the range of values up to some particular value of the random variable, integrating the PDF, sorry. Where we've got a bivariate distribution, we can write in slightly different notation what I was using before with the cumulative. Hang on a minute. Oh, just a minute, I'm lost on this myself. Oh, sorry, yeah, I got it. We can specify the value of the other variable and integrate over the first variable, and similarly get the cumulative for the get the cumulative from the probability density function of the second random variable. Okay, now we can use that, I think, to make it a bit clearer what's going on rather than dealing with the rather more general forms we had before. At least I'm hoping this is going to help you. Let's just try looking at an example If we look at exercise 3.7, we're told, excuse me, we're told that the marginal cumulative distribution is obtained by looking at the probabilities in X up to some particular value in its support, but looking at all of the values, or factoring in that, it's not going to work, is it? Factoring in the whole range of values that the second random variable might take. Now, in essence, that means that we're going to integrate from the lower range from the random variable X up to the given value, the little x, the thing here, while integrating entirely over the range of values that the second random variable can take. But that's effectively the same as saying we're going to look at the PDF for X and integrate over its values up to whatever the limit is, in this case, little x. Now that tells us something that we can use, and something that you will need to get in your minds and have in your minds for the examination, because it doesn't appear in the usual results and formulae at the back of the exam papers each year. It means that if we were to take the limiting value over the joint probability, that is, looking over all the values of the second random variable, then what we're doing is we're getting a cumulative distribution for the first variable, and similarly the other way around for the second random variable. So you set the upper value of one variable to be, well, whatever the upper limit is, in this case plus infinity, to get the marginal distribution for the other variable. Okay. Interesting and intuitive sort of idea that the examiners expect the statistician will know, so it won't be in the usual results and formulae. Right, as promised, I know this is a bit backhanded, but let's have a little look at what we mean formally by conditional distributions. Well, it's the obvious. Y given x equals x means we look at what y does given that x is fixed at a particular value, little x. That is, we take a value as taken or fixed for x. Okay. And we look at what the distribution of y values are given that fixed value of x. And we can do that for any value of the random x, can't we? And it's sort of interesting to us because the distribution of y might differ quite markedly as we change the value of x. That is, for fixing the random variable x at x1 might give us a different distribution than fixing the value of x to be x2. And the examples given in the materials is this rather graphic, well, this rather picturesque example of height being conditioned by age. Right? For quite a young child, height will be shorter than it is for an older child, and that'll be shorter than it is for the parent. And as I know to my cost, my three sons have grown up to all be taller than me, so there's a sense in which the height being conditioned on age turns over time. Yes, a relatively easy, straightforward way of defining conditional densities. You start with the joint density, thing in that top line there, and you divide by the appropriate marginal. So if we want to get y given x, we start with the joint density and divide by the marginal in x. That is the thing that we're fixing the values for. And of course that works provided the marginal, the PDF for X is greater than 0. It can't be 0. Yeah, something happened here. Where is it? Oh, I see. What's going on? Wait, okay. At real-time editing. Now, what we're really saying here is the marginal X is just change. It'll only change when you change X. So doing that normalisation, though, tells us that if we integrate over the full range of Y values, then the conditional thing must have value 1. That is, the conditional distribution is a probability density function. Okay, satisfies both conditions required to be that. Well, yeah, okay. I've endeavoured here to give you some sort of motivation and hopefully it'll help it stick in your mind. The density of Y given X has the same shape as the cross-section of the original joint density, but where we fix the value for X. So that is, there's a normalising constant, and apart from that normalising constant, we're just getting back the joint distribution values. And the example, as ever, it seems in this early part of the materials, the example is to do with the standard bivariate normal. Now, I won't take you through it. If that's the joint, the standard bivariate normal, then the for it in there. And then I go on with this particular standard normal distribution, and then the manipulations in the question tell us it's that. And we can do something similar with the distribution of X conditional on Y. I think this might be where I'll stop answering one of the questions, the joint distribution back by looking at a conditional and a marginal. And I think I'll save this for another session. All right. Okay, have there been any questions on this material I've embarked on since I changed over to the second part of the presentation? Are there any issues, questions? David knows I forgot to press button, but I have this to record. And what happens is that it sometimes takes a day or two for recording to come out and be posted amongst the list of the recorded sessions, but it will be there somewhere in the next couple of days. Okay. Yes, I sent the slides to you already. Sent them out in an email either just before or just after the actual session. Stephanie, I did send them out, as I was just saying. Are you in my group? And that might be why you haven't got them. If you haven't got them, send me an email with your email address. Sorry, send me an email from your OU email address and I'll send it back to you, okay? Okay. Okay, Richard, will you send me an email and I'll get the slides back to you. All right. Good. And I suppose the thing I should say to you all is, of course, there's a couple of hints down the bottom of these slides on doing TMA question 2. And I've already told you about TMA question 3 in the previous session. Well, if there's nothing else, we could probably call it a night and go about the rest of our evenings. I hope your evenings are good.